linear transformation. So first of all, what is linear operator? A linear operator is an operator such that the domain of this operator is a vector space and range of this operator lies in a vector space over the same field. Suppose x and y are elements of domain of this operator and alpha is any scalar, then t of x plus y is equal to t of x plus t of y. X and y are elements of domain of t, tx and ty are elements of range of t, and t of alpha x is equal to alpha times t of x. So this formula expresses the fact that linear operator t is a homomorphism of a vector space into another vector space. Means t preserves the two operations of vector space, addition and scalar multiplication. On the left side, first we apply a vector space operation, addition or scalar multiplication, and then map the resulting vector into y. Suppose first of all we will add x and y, then we will operate the operator t on it to obtain the resulting vector. Similarly, in this case, first of all we will multiply x by scalar alpha and then we operate t on it to get the resulting vector in y. Whereas on the right we first map x and y into y. We will operate x on t and then we will operate t on x and then we will operate t on y, and then we will add the resulting vectors. Here also first we will operate t on x and then we will multiply the resulting vector by alpha. So on the right side, first we map x and y into y and then perform a vector space operations, like here we operated addition and here we operated scalar multiplication, but the outcome is the same, and these two conditions are equivalent to a single condition, t of alpha x plus beta y equal to alpha tx plus beta ty. Now the null space. The null space of operator t is the set of all x belonging to NT. NT means null space of t such that tx equal to 0. Bounded linear operator. Let x and y be norm spaces and t is the operator from domain of t to y. Suppose this is a linear operator where domain of t is a subset of x. Then operator t is said to be bounded if there is a real number c such that for all x belonging to domain of t, norm of tx is less than or equal to c times norm of x. Here norm on the left is that of y and the norm on right is that on x, but for simplicity we have denoted both the symbols by the same norm. It shows that bounded linear operators maps bounded sets in dt onto bounded sets in y. Suppose if a norm space X is finite dimensional, means it has finite number of bases, then every linear operator on X is bounded. Suppose dimension of X is n and E1, E2, En, the set consisting of these is a basis for X. So we can write X as alpha 1 E1 plus alpha 2 E2 plus alpha and so on up to alpha and En. Because this is a basis set, so it can be expressed, any element of X can be expressed as a linear combination of its elements. So X is equal to alpha 1 E1 plus alpha 2 E2 plus so on up to alpha and En. And if we write it in summation form, we can write it as sigma alpha j Ej, where j varies from I to n. If we consider any linear operator T on x, because T is linear, therefore norm of Tx is equal to norm of Tx is sigma alpha j Ej, here this term. So we can write it as, if we can take sigma out and this alpha j as mod alpha j, and we can write norm of Tej. If we fix these j's, here j's varies from 1 to n, if we fix these, that it will be less than or equal to maximum k norm of Tk, sigma alpha j, and this is less than or equal to 1 upon c sigma alpha j Ej. This is same, and this term is less than or equal to 1 upon c sigma alpha j Ej, where c is a constant, ensuring that the basis vector have unit norm, means norm Ek is less than or equal to c, and this is equal to this is norm x, because x is equal to sigma alpha j Ej, so this is equal to norm x. So it is maximum k norm Tek 1 upon c norm x. It means this norm Tx is less than or equal to beta times norm x, if we substitute this term to be beta. So beta I have taken to be 1 upon c maximum of k norm Tk, and it shows that T is bounded. Now continuity. Suppose T is any operator from domain of T to Y, here domain of T is a subset of X, where X and Y are normed spaces. The operator T is continuous at X naught belonging to domain of T if for every epsilon greater than 0 there is a delta greater than 0, such that norm of Tx minus Tx naught is less than epsilon for all x belonging to domain of T, satisfying norm x minus x naught less than delta. And this operator T is continuous if it is continuous at all the points of domain of T. Now we have one result which relates continuity and null space. Suppose x and y are normed spaces over the field K, and T is a operator from x to y, and it is a bounded linear operator, then xn tends to x implies Txn tends to Tx, where xn and x belongs to domain of T, which is subset of x. Xn tends to x implies Txn tends to Tx is same as it denotes the continuity of T, because by definition T is continuous if xn tends to x implies Txn tends to Tx. So it is same as the continuity of T. And second is that null space NT is closed. So we will prove these two results. So to prove the first result, we see that norm of Txn minus Tx is equal to norm of T of xn minus x, because T is linear operator, and this is less than or equal to norm T norm xn minus x, but it is given that xn tends to x. It means xn minus x tends to 0. If xn minus x tends to 0, it means whole term tends to 0. If this term tends to 0, it means Txn minus Tx tends to 0, or we can say Txn tends to Tx. It means T is continuous. Now we have to show that NT is closed. Null space of T is closed. Suppose X belongs to closure of null space of T. It means there is a sequence Xn in null space of T such that Xn converges to X. If we consider any sequence Txn, then we know that by this result, if Xn tends to X, then Txn tends to Tx, means T is continuous. So we have considered Xn tends to X. So this Txn also tends to Tx by previous result, because T is continuous. So Txn is equal to T of 0, and T of 0 means 0 for all n, because Xn belongs to null space of T. By the definition of null space, it means Txn tends to 0. It means here we have written Txn tends to Tx, here we have written Txn tends to 0. It means Tx is equal to 0, and it means X belongs to null space of T by definition of null space. So we had chosen X to be arbitrary element of closure of null space of T. It means null space of T is closed because it belongs to X belongs to NT, means it contains all its limit points. So it means null space of T is closed. Now equality of two operators. Two operators T1 and T2 are defined to be equal if they have the same domain and if T1x equal to T2x for all x belonging to their domains, and we write it as T1 equal to T2. For two operators to be equal, first of all their domain should be equal and their range at any point of the domain should be equal. Now restriction. The restriction of operator T from domain of T to Y, where B is a subset of dt, is denoted by T. We write this line, straight line, and write B in the suffix. We denote restriction of T to a subset B like this, and the restriction of an operator to a subset B is the operator defined by this from B to Y, such that TIBV x is equal to Tx for all x belonging to x. And what is extension of T? Extension of T to a set M which contains domain of T is an operator. We have denoted it by T bar, which is from a set M to Y, such that restriction of T bar to a subset dt is equal to T. That is T bar x equal to Tx for all x belonging to dt. Here it means T is the restriction of T bar to domain of T. A functional is an operator whose range lies on the real line R or in the complex plane C. And what is isomorphism? An isomorphism of a norm space X onto norm space X bar is a bijective linear operator. Bijective means 1 1 as well as onto, which preserves norm. That is, for all x belonging to x, norm of Tx is equal to norm of x. Hence T is isometric. X is called homomorphic with x bar, and x bar are called isomorphic normed spaces. If we talk about metric spaces, an isomorphism T of a metric space xd onto another metric space x bar d bar is a bijective mapping which preserves the distance for all xy belonging to x. Means preserves the distance means distance between Tx and Ty is same as distance between x and y. In this case, x bar is called isomorphic with x. In case of metric spaces, we say that it preserves the distance. And here in norm spaces, we say it preserves the norm. Means norm Tx equal to norm x. Although we know that how to define a metric in norm spaces. Both these definitions are equivalent. Suppose we have two Banach spaces B and B dash, and T is a mapping from B to B dash is continuous linear transformation of B onto B dash. Then T is an open mapping. Means if T is continuous linear transformation of Banach space B onto B dash, then T is an open mapping. So it is given to us that T is continuous linear transformation from a Banach space B onto Banach space B dash. Suppose U is open set in B, in Banach space B. Now we have to show that T is an open mapping. To prove this, it is sufficient to show that image of this open set U in B is open in B dash. Now let Y belongs to TU,
I found this on the web.
which is image of open set in B. So it means there exists X belonging to U such that Tx is equal to Y, because it is given to us that T is onto. So onto means every element in B dash have a pre-image in B dash, at least one pre-image in B. So Tx is equal to Y, because every element Y belonging to T, for every element Y belonging to TU, there always exists element X belonging to U such that Tx equal to Y. This is by definition of onto. We know that U is open. It means there exists an epsilon greater than 0 such that the ball B centered at X and radius epsilon is contained in U. This is by definition of open set. Now we have to show that TU is open. So if we consider the open ball B dash centered at Y and radius epsilon, then it is sufficient to show that this open ball is a subset of TU. Suppose Z is any point in this open ball centered at Y and radius epsilon. So by definition of open ball, it means norm of Z minus Y is less than epsilon. Suppose we consider another open ball X centered at X and radius delta. Because U is open, therefore this ball is a subset of U. Let X dash belongs to this ball centered at X and radius delta. So by definition of open ball, we have norm of X dash minus X is less than delta. But T is given to be continuous mapping, continuous linear transformation. So by continuity of T, it means norm of Tx dash minus Tx is less than epsilon. But Tx is equal to Y. It is here. So if we write Tx equal to Y, then we can say norm Tx minus Y is less than epsilon if norm X dash minus X is less than delta. This implies Tx dash belongs to open ball centered at Y and radius epsilon. It means for any Z belonging to open ball centered at Y and radius epsilon, there exists an X dash belonging to open set U, or to be specific, X dash belongs to open ball centered at X radius delta, which is a subset of U, so that Tx dash equal to Z. This Tx dash is equal to image of X dash under T is equal to Z. What does it mean? It means that open ball centered at Y and radius epsilon is subset of TU. So by definition, it means TU is open in B dash. TU is open in B dash means T is an open mapping. Now one more result. On a non-empty subset of a norm-linear space N is bounded if and only if Fs means image of S is bounded set of numbers for each f in n star. N star means dual of n. Dual of non-space is the space of continuous linear functionals. So we are given a non-empty subset of a normed linear space n. Let S be, and it is bounded. Let S be bounded subset of n. It means there exists a positive real number m such that norm of x is less than or equal to m for all x belonging to S, because S is bounded subset of n. Suppose f belongs to n star. It is given, since f is continuous linear functional, because it is in n star, it is in dual of n, and dual of non-space is a space of continuous linear functionals. Therefore, because f belongs to n star, it is continuous linear functional, so it is bounded on bounded subsets. So it means there exists a positive real number kf such that modulus of fx is less than or equal to k times norm of kf times norm of x. For all x belonging to n. It means for x belonging to S, modulus of fx is less than or equal to k times kf times norm of x. But norm of x is less than n. So it is less than or equal to kf times n. So it means fs is bounded for each f belonging to n star, because modulus of fx is less than or equal to kf times n. So we have proved that S is non-empty. If S is non-empty bounded subset of normed linear space n, then Fs is bounded set of numbers for each f in n star. N star means dual of n. Now for the converse part, suppose Fs is bounded for each f in n star. Now we have to show that S is bounded. Suppose we assume that S is not bounded. It means for each positive integer n, there exists xn belonging to S such that norm of xn is greater than or equal to n. So consider the functional f belonging to n star defined by f and x equal to norm x upon n for all x belonging to n. So it means modulus of this f and xn is equal to norm of xn upon n, and it is greater than 1, because norm xn is greater than n. So it is fn x is equal to norm x upon mod n. So fn xn is equal to norm xn upon n, and it is greater than n because norm x is greater than n. N upon n will cancel out, and it is greater than n for all x belonging to n. So what does it shows? Modulus of fn xn is greater than 1 means fn s is not bounded for any n. But we have assumed that fs is bounded for each f belonging to n. So our assumption that s is not bounded must be false, because it is given to us. Hence s is bounded if fs is bounded for each f in n star. So to prove this result, we have made use of the fact that dual of normed linear space is the space of continuous linear functional, which we have used it here, and in this case n star denotes the dual of n. In a normed space N, given a non-empty subset M, there exists continuous linear functional f in the dual space N star such that f of M equal to singleton set 0 and f of x naught is not equal to 0 for x naught belonging to M. N is given to be nonlinear space, M is non-empty subset, and f is continuous linear functional in the dual space N star. Let x naught be fixed element in M. Suppose A is equal to its complement means M minus x naught, which consists of all the elements of M except x naught, because x naught belongs to M because it is its fixed element and x naught does not belong to A. We know that complement of a single point in a normed space is closed, so it means A is closed set. And x naught does not belong to A. So by Hann-Banach separation theorem, there exists continuous linear functional f in the dual space N star such that image of all the elements x belonging to A under f is 0 and image of x naught under f is not equal to 0. So it means fm equal to singleton set 0 because fx is 0 for all x belonging to A. So it means fm is equal to 0 since fx equal to 0 for all x belonging to A and x naught is the only remaining element in M. Hence we have constructed continuous linear functional in dual space N star such that fm equal to 0 and fx not equal to 0 as it was required to prove. And this result says that there exists linear functional that assigns 0 to entire set M except for a particular element x naught where it takes non-zero value. Now let x be a Banach space and Y be a normed space over a field K. If F denote boundary linear operators from x to y is pointwise bounded, then it is uniformly bounded. Suppose An denote the set consisting of all the elements x belonging to capital X such that supremum of norm Tx is less than or equal to n for all t belonging to F. F is a set of boundary linear operators from x to y. So it means union of An where n belongs to n is equal to x. Let xk belongs to An and suppose xk converges to x in x. It means norm of Tx is equal to limit k tends to infinity norm Txk and it is less than or equal to n for all t belonging to F so that An is closed for every n belonging to n. Because n is a natural number, x naught belongs to An and epsilon is greater than 0, so it means closure of open ball centered at x naught and radius epsilon is contained in An. Suppose Z belongs to ball centered at 0 and radius epsilon. So we have x minus z and x naught plus z belongs to this ball centered at x naught and radius epsilon, and this ball is contained in AN, and it means norm of Tz is equal to norm 1 by 2 z plus x naught plus 1 by 2 z minus x naught. We have added half x naught and subtracted half x naught and expressed z as half z plus half z. So by triangle inequality, this is less than or equal to 1 by 2 norm t z plus x naught plus 1 by 2 norm t x naught minus z. And suppose this is less than or equal to n. So 1 by 2 n, this is less than or equal to n. So n by 2 plus n by 2 is n. So norm of Tz is less than or equal to n. Finally, suppose x belongs to x with norm x less than or equal to 1. Suppose z is equal to epsilon x, and this belongs to the ball centered at 0 and radius epsilon. It means n is greater than or equal to norm Tz, because norm Tz is less than or equal to n. It means n is greater than or equal to norm Tz, and this is equal to epsilon times norm Tx, because z is equal to epsilon x. So it means supremum of norm T is less than or equal to norm epsilon. Shift this epsilon to this side. So supremum of norm T is less than or equal to n upon epsilon for all t belonging to F. So it means if a set F of bounded linear operators from x to y is pointwise bounded, then it is uniformly bounded. Now one more result. If B and B dash are two Banach spaces and T is a linear transformation from B onto B dash, then T is continuous mapping if and only if its graph is closed. Suppose T is continuous, then we have to show that its graph is closed. Suppose T is continuous, it means if there is a sequence xn converging to x, then it means txn converges to tx. This is by definition of continuity. Now we have to show that graph of T is closed. Graph of T means, if you denote the graph of T by Tg, it is a set of all the ordered pair x and tx. Tx means image of x under T such that x belongs to B. This is the graph of T, set of ordered pair x and its image. We have to prove that this graph is closed. To show that this graph is closed, suppose xy belongs to its closure, means Tg bar. Because xy belongs to closure of Tg, Tg is the graph of T, so there exists a sequence xn txn in graph of T, so that this sequence converges to xy. But we know that xn tends to x and txn tends to tx from here. So it means this tx and y are equal, means y is equal to tx for x belonging to B, and it means x tx belongs to Tg. It means it contains all its limit point. It means Tg is closed. Now converse. We assume that Tg is closed, means graph of T is closed. Now we have to show that T is continuous mapping. Now consider the sequence xn txn in the graph of T. It is the sequence of ordered pair xn and its image under T, which belongs to graph of T. Now we have it is given to us that graph of T is closed. It means any limit point of this sequence must also belongs to graph of T means Tg. Let this sequence xn txn converge to xtx, and this belongs to Tg as x belongs to b by definition of graph. So this implies Tx belongs to b dash. It means Tx belongs to b dash, xn tends to x, txn tends to tx, and Tx belongs to b. It means txn converges to Tx in b dash. And this result which states that the linear transformation of b onto b dash is continuous, mapping if and only if its graph is closed, is a characterization of continuity for a linear transformation T from a Banach space B into another Banach space B dash. Now this is one more result. Although this result is from the previous lecture, it was left by mistake, so I have included it here. Suppose T be an arbitrary operator on a Hilbert space H, and if alpha and beta are scalars such that modulus of alpha is equal to modulus of beta, then alpha t plus beta t star is normal. We know that any operator T is normal if T star is equal to T star T. So we had to prove that alpha t plus beta t star equal to normal is normal. We need to show that if we assume it to A, then we have to show that A star is equal to A star A. Means alpha t beta t star whole star is equal to alpha t plus beta t star star into alpha t plus beta t star. First we will check its left hand side. So left hand side is equal to alpha t beta t star. This is same, and because we have star here, so if you open this will be alpha bar t star plus beta bar t. So if we multiply these two, we will get alpha t alpha bar t, alpha t beta bar t, beta t star alpha bar t star, beta t star beta bar t. And we can write it as alpha bar tt star, alpha beta bar tt, beta alpha bar t star, beta bar t star t. It is given to us that mod alpha is equal to mod beta. So it means alpha square equal to beta square, or alpha bar equal to beta bar. So we can write it as alpha square, we can write it as alpha square, because these two are equal. Alpha bar is equal to beta bar. So if we write it alpha square, we can take it common. So alpha square t star, and this is t star t, and here we have two terms, alpha beta bar tt, beta alpha bar t star t. Now the right hand side. Now for the right hand side, alpha t plus beta t star star, alpha t plus beta t star is equal to alpha bar t star plus beta bar t, alpha t plus beta t star. If we multiply these, alpha bar t star alpha t, alpha bar t star beta t star, beta bar t alpha t, beta bar t beta t star. So alpha bar alpha means alpha square t star t, alpha bar beta t star t, beta bar alpha dt, beta bar beta t star. Because alpha square is equal to beta square, we can take it common, alpha square t star t and plus tt star, and this is alpha bar beta t star, beta bar alpha tt. These terms are same. Here alpha beta bar tt, this is beta alpha bar t star, beta alpha bar t star. We note that scalar multiplication commutes. Also tt star plus t star t is equal to same as t star t plus tt star. So it means this left hand side is equal to right hand side. So we have proved that alpha t plus beta t star is a normal operator on a Hilbert space H. Thank you.